Sorry for the long wait. We've had some technical problems. Damn IBM ThinkPads, I don't know. I guess Rainforest Hope had some problems with his at the last CanSec West conference, and it looks like we're having the exact same problems. Anyhow, we think we've got a workaround.
Does this work? Yeah, now it works. Excellent. So, yeah, we will be talking about FireWall 1, and I have the pleasure, well, my name is Thomas Lepatik. I have the pleasure to be here with Doug Song and John McDonald, two really smart guys, and we will be showing you some things that we used during the past few months to go through FireWall 1 installations, real-world installations that is. We have put a lot of research into that because John and I are at a consulting company, and we have found that our customers, they just have FireWall 1 installation, and that's why we had a closer look at it. And well, we found some interesting stuff that we're going to share with you today. We have changed the whole concept of the presentation a bit because we thought it might make more sense to make certain things first and delay certain other things. So you will have to do a bit of jumping between different pages because we have reordered our PowerPoint presentations, whereas your folders have not been reordered.
It's more fun this way.
But I think it will still work. So what we have been looking at in the beginning was Checkpoint FireWall 1 version 4.0 Service Pack 5 because, well, we were using the Nokia IP440 that you can see here, and it always took a while in the past until Nokia made those latest versions available. The interesting thing is that about 4 weeks before the conference, well, we intended to give Checkpoint notice of what we are going to present. 4 weeks before the conference, we wanted to give them 4 weeks to fix everything and then come up with fixes on this day today. They contacted actually us, so we didn't have to contact them, but they contacted us, and they were very, very cooperative, and they provided us with the latest version also for the Nokia firewall, and we were able to verify our findings with version 4.1. So it turned out that many of the things still applied, whereas some other things apply in a slightly different way. But we will tell you all that when we are giving the presentation. So I'll be giving a quick overview. Well, the overview is still according to how it should have been in the beginning. I will give a quick overview of the architecture, and we would like to first go to the fifth point, which is attacking the authentication mechanism between FireWall 1 modules. We'll do that first, and then start at the beginning again, attacking the firewall state 1, FWZ, encapsulation, and then attacking the firewall state part 2, and at the end, hardening firewall 1. And well, the big picture is actually something that we will do in the beginning as well, because the big picture is something we have found that the attacks that we have found in FireWall 1 perhaps also apply to other firewalls, because it's the results that we obtained can be transferred to other firewall products probably. And this is why we want to give this first, so that you get the big picture first, and after that we are going to show you how the whole thing will work with FireWall 1. Okay, this is the topology of our test setup. In the middle one, the brick wall, is the symbol for our firewall. It might be well the case, you're looking for it, it might be well the case that it's not in the folder, because if you haven't been given additional sheets of paper, because we have actually added 2 slides that you will not find in there, so I don't know whether they have been distributed among you. If not, then you have to, well, you just try to learn it by heart and remember it. So in the middle, this is the FireWall 1 module. The interesting part is the IP addresses of the Solaris box back there and of the Linux box back here. So this is basically the 2 IP addresses that you need to memorize. We have the IP440 in the middle, which is running FireWall 1 service version 4.1 Service Pack 1. On the left-hand side, we have the Solaris box, which is the Solaris 2.6 box, which we are going to exploit. This is the Solaris box that is protected by the firewall, and we will go through the firewall and attack this box in order to gain access to it. On the right-hand side, and the 172.16 network is the victim network. Then we have the attacker's network. It's the 192.168 network, consisting of a Linux box, which is the attacking machine, of an OpenBSD box, which runs FragRouter, something probably known, written by Doug Song. It's on the OpenBSD box, and In order to show you authentication problems that exist between firewall modules, we have installed on the Windows NT box up there. It's not only running the presentation, it's also a packet filtering module, a FireWall 1 packet filtering module. So we have on the Nokia IP440 a packet filtering module, we have a management module, and on the Windows NT box we just have a packet filtering module. And we will show you how we will be able to unload, for example, the security policy from the filtering module by bypassing the authentication mechanism that normally exists between those two modules. Okay, this is the place where Daxong will take over.
In general, what we're looking at are problems in inspection when looking at how to attack these firewalls. We've identified 4 basic avenues of attack, and these are all basic constraints in inspection that can be exploited to get through firewalls sometimes. Specifically, the first being unreliable or unauthenticated input. Maybe it maps to what's called input validation error in like the bug track BID or taxonomy. But we just consider this to be reliance on input that potentially could be spoofed, forged, what have you. The second is layering restrictions on inspection. Because of the way that the network protocol stack is architected, you have certain abstraction layers which you really shouldn't violate if you want to stay within the spec, and sometimes that limits actually what you can filter on. Layering violations in inspection is sort of the inverse problem, where when you do actually violate these abstraction layers, you cause problems for yourself because you look at things out of context, and we'll examine that also. And the last being ambiguous end-to-end semantics, sort of a problem that also affects network IDS systems, where the box in the middle the firewall in this case, isn't interpreting correctly what's being sent from the attacker to the end host, as interpreted by the end host. So sort of as a hokey example, we have airport security. Every airport has a security checkpoint where they try to make sure that you're not sending bombs to somewhere else or blah, blah, blah. And just like a firewall checkpoint, or checkpoint firewall, it has problems. The first might be, going by our sort of loose taxonomy here, examining baggage tags. If you were to just determine the security of a parcel that someone's trying to send via an airplane by looking at who's sending it, that's probably not really a good idea. Someone could just switch the tags. Layering restrictions on inspection, sometimes you're not allowed to look inside the bag for what's actually in there, so you can only examine the external characteristics, shape, size, weight, what have you, and this sort of corresponds to the limitations you have in looking at the network packet headers, for instance, not looking at TCP headers within IP packets. Layering violations in inspection, if, for instance, you came with 5 bags, you happen to have a bomb, but it was spread out across those 5 bags, each checked by 5 separate guards, you didn't find a whole bomb in there, it might get through. This is sort of a serialization issue, and this also maps pretty cleanly to attacks we found. And again, ambiguous end-to-end semantics, checking only for known contraband. Someone could be sending a completely other kind of, I don't know, dangerous device or something that you don't know about, and if they don't recognize it, they just let it through. So in general, this is the classification of attacks that we're presenting. We have found attack against TCP fast mode, which isn't used much anymore, I think, by most people. But allows you to do certain things, mostly just port scanning. Layering restrictions on inspection, this is the class of attacks dealing with FWZ encapsulation. Layering violations in inspection, FTP data connection handling, unidirectional TCP data flow, and RSH connection handling are 3 examples that we found. There are probably many others because of the way Checkpoint does its, I guess, application proxying. By looking at data within discrete IP packets. And the last, parsing of FTP port commands. As it turns out, the checkpoint firewall does it a bit differently than some FTP daemons do, and we can exploit that as well.
Okay.
Thomas?
That's where I will take over again. So, Like I said, we start with the inter-module authentication. FireWall 1 installations can be distributed. That means you have a management module, a centralized management module, which is controlled by the graphical user interface. All the communication between the graphical user interface and the management module is done via port 258, 258 TCP connections, and the management module talks to the filtering modules via connections that are to port 256 TCP. So what is being done between the management module and the filtering modules? Policies are uploaded, policies are unloaded, and this is exactly what we are going to do. Status polling is done, and logging is done by the filtering modules to the management module, for example. So all this takes place via the service at port 256, and of course, in order not to be able, or in order to prevent attackers from uploading security policies or unloading security policies, authentication is performed. Basically, there are three authentication forms. It's S-key, which is a variant of the S-key mechanism that we all know from logging onto machines. Then they have something proprietary, which is called FWN1, and something proprietary that is called FWA1. However, in the future, everything will be replaced by SSL, and yeah, this is a good idea, replacing this by SSL. The reason for that is something that we will see right now, because we will be able to circumvent all three different kinds of authentication. They are broken in a way that enables an attacker to impersonate a management module in order to send commands to the filtering modules, commands like unload security policy, for example. Okay, let's start with a general overview of the protocol between the management module and the filtering modules. In the beginning, so we have the management module on the left-hand side and the filter module on the right-hand side. And we will be going to impersonate a management module in order to access the filtering module and unload the security policy. First of all, we send a version, protocol version. We get a protocol version back from the filtering module. Then we send to the filtering module the command. In our case, it's the unload command. We send to the filtering module our IP addresses, the IP addresses of all our interfaces, and we get back a list of IP addresses of all the filtering modules' IP addresses. So after that, the filtering module tells us in which way it wants to authenticate. That is S-key, FWN1, FWA1. And we authenticate, and then we pass the arguments to the command and get the result, and we are done. So this is basically how it works for all commands. This is basically the framework, and we will now concentrate on how the authentication mechanism works, because this is where we're going to attack. Oh, and there's another interesting thing that I almost forgot. When the filtering module identifies us, it doesn't look at the IP address where the connection comes from. It just looks at the IP addresses that we pass to it. So we can do this from anywhere in the world. The idea is, it's actually probably, it has the background that if the management module has more than one interface, people were configuring on the filtering module an authentication key for the wrong interface, and the management module connected to the filtering module with another interface, and the filtering module said, no, I don't have any authentication key for that source IP address. So this is probably the reason why the management module transmits all of its IP addresses, so that the filtering module can check all of the IP addresses and look at its authentication keys in order to find one that corresponds with any of these IP addresses. So this is probably the reason for that. So the first thing is S-key authentication. Many among you are probably familiar with the way how S-key works. I'll nevertheless shortly outline it again. S-key is based on an iterated hash. An iterated hash is if you have a secret, so it's based on a shared secret. The point of authentication, that is my peer that I want to authenticate with, knows the secret and I know the secret. I hash the secret once. This is the first iteration. Then I take the result, hash that again. This is the second iteration. The result of that can be hashed again, hashed again, hashed again, hashed again. This is the iterated hash. This is what I write down as hash and then the index n. So it's hash n means the hash has been iterated n times. So this is exactly what you see in the uppermost line. So a nice property of that is trivial. If you have hash 10, for example, you can just iterate it once and get hash 11. But if you have hash 11, then you can't go back. You can't get from that, you can't get hash 10. Always under the condition that hash is a cryptographically strong hash function like MD5, for example. So if I have MD5 iterate that 11 times, I can't go back from the result to MD5 iterated only 10 times. But I can go forward. If I have MD5 iterated 10 times, I can iterate the result once and get MD5 11 times iterated. So the basic principle is pretty simple by SKey. I have a secret here, the seed X on the left-hand side, and my peer that I want to authenticate with knows hash 100 of X. So it knows the value of X iterated in the hash 100 times. What it is going to ask me on authentication, it's going to ask me for hash iterated 99 times. So anyone who knows hash 100 can verify my reply to that because I know the seed. I iterated 99 times, send the result to my peer. My peer knows the result after 100 iterations. That is, it gets what it takes what it got from me, iterates the hash once, gets hash 100, and can thus verify that I am in possession of the correct seed X. So with hash 100, knowing hash 100, you can verify iterations with a lower iteration count between 1 and 99, but you cannot generate them. Knowing hash 100, you can't generate hash 99, but getting hash 99, you can verify with hash 100 that it's really been calculated using the seed X. So this is done. It asks for hash 99, it asks for hash 98, hash 97, whenever I connect to it, and whenever authentication is performed. So eventually, it will reach an index of 1. So it asks me for hash 1. The peer sends hash 1 to the authentication peer, and now this SKey chain, as we call it, the 100 different one-time passwords that we have generated using the iterations have been used up. So what do we have to do now? We have to calculate a new seed, and the new seed has to be created with enough entropy so that nobody's able to guess it, because I generate the authentication peer on the left-hand side calculates a new seed Y, calculates hash 100 of Y, and transmit this to the FireWall, to the filtering module. So the filtering module now knows hash 100 of the new seed and is able to verify hash 99 of the new seed, hash 98 from the new seed. So what we end up is a new SKey chain. So the problem with that is, the principle is nice, but the problem with that is that the new seed doesn't contain very much entropy. It's basically a function of time, and time in a resolution of seconds. That is, if you can predict with a precision of seconds when the new seed Y was generated, then you're able to predict the key, and you're able to impersonate somebody who is actually in possession of the seed Y. So what we are able to do is we can just brute force this authentication because the search space is pretty small. You must imagine, for example, you have a FireWall module that authenticates using SKey. That means if you start a logging process that polls the status, if you start the status program, then the status of the FireWall module will be polled every 10 seconds. That is, one SKey chain is used up within 1,000 seconds. 100 different passwords is what we have, plus the 10 seconds interval, which leads to 1,000 seconds. That is 3 times an hour the key is being changed. So if I want to guess the key, I only have to go back from current time at maximum a third of an hour, and I will be able to guess that. And this is exactly what we're going to do now. We will be guessing a key. So the first thing that I would like to show to you is the security policy. It's pretty straightforward. We have, like I said, 2 filtering modules. One is the NT box on the top of it, so this here corresponds very nicely to the picture that I've shown before. This is the Spark, and we have the NT computer up here, the IP440 down there, and I have configured SKey authentication between the management module on the IP440 and the filtering module on the notebook computer. And all we have is we have FireWall 1 control connections enabled to both of them. So this is FireWall 1 control connections. That is a standard configuration for version 4.0. It has been changed in 4.1. I will be saying something about that later. But for now, we have control connections enabled to both of them. We drop everything from and to TL2. TL2 is the upper computer. It's the Win and T machine. And we accept everything from and to the IP440. So the IP440 will not play any role in this demonstration now. We will just demonstrate that we can download or unload, the security policy from TL2. For that, I will be using. I will first show you how it looks in a legitimate case. So I have another window here that directly goes to the IP440, and I can here on the IP440. Perhaps I should make it a bit larger, the font a bit. I will not mess up anything. I will unload the security policy just to show what it looks like from the .149 address, which is the Windows NT machine. That's how it looks if it is unloaded legitimately by the FireWall 1 command line tool. So I have configured S-key authentication using a seed with the put key command, as you do it on FireWall 1. So what we can see here is, move down there. In the fourth line, you see that it authenticates with a key test. It has the my address. It's the 194.221.6159. This is the address of the IP440. It says, hey, I'm the IP440, and the challenge is 6. That is, it wants to know the seed, the challenge for the 6 iterations. So it calculates a reply, and then it is authenticated and goes through it and completely unlocks the policy. So the interesting part comes when I now do it again, because then a count of 5 passwords will be left. Unload my screen. So we see the same thing again. We will now see that it's not asking for challenge number 6, but for challenge 5. And at the same time, it will generate a new seed. It doesn't wait until the challenge, until the iterations count has reached 1, but it does so. No, it doesn't do that. It doesn't when it's 4. So let's unload the policy again. This time it should generate a new key, and this is exactly what we are going to attack. Okay. So because the idea is that whenever you configure a shared secret on both stations, it will be not used 100 times because they're probably afraid of users choosing bad passwords, but it will be used only 2 times, and then a new password will be generated. So, okay, this is where we see it. It's very nice. Up there again, okay, it wants S-key authentication. Then we see that it asks for a challenge 4. This is what you see here in almost the middle of the screen. Challenge 4, it identifies itself, calculates a response, and FW key put, it generates a new key. You see that? This is exactly where it generates a new key, and this is the new key that we would need in order to impersonate the module. And we have a small program that will be able to do that. We just need here the current time on that computer. It's another time zone, so it's 10 in the evening. So to make it quick, I'll just adapt the test to the demonstration to this date and this time. So what we are going to do now is we simply use a tool to try all the values from 5 minutes ago to now. So the tool is called FW1 brute force, FW1BF. You see the usage here. So the firewall address that we want to attack is 149.149. This is the firewall module here on the Windows NT machine. So we will reinstall the policy so that you see the effect. Reinstall the policy here. In the meantime, 149, we want to impersonate 194.221.6159, which is the management module. And we want to try values from year 2000, July 26th. We said here it's 20 10 in the evening, at 10:15 approximately. So we have only one thing to look at because this computer here is another time zone, so we have to subtract 5 hours from the time. So we say we want to try all values from 5 in the evening, so 1700. We say like 1714, or let's go from 1710. 002, year 2000, July 26th, 17 and 20 minutes. So we go from 10 past 5 to 20 past 5 and try all the combinations. And we do that with 3 processes in parallel. We can specify this, and that's where it goes. You see down here, it tries all the passwords. And it does so by connecting to the Windows NT machine, trying the password, and if it's being rejected, it tries the next password. So this is a bit slow, although we could increase the number of processes. Version 4.1, which we're using now, doesn't handle very many processes in parallel. So with version 4.0, though, you could run about 30 to 40 processes in parallel, which enables you to go through quite a lot of keys in quite a short period of time. That is, even if the key regeneration, the automated, took place 1 week ago, you would still be able to guess the key just by quickly going through all the possible values. So, well, we know the key because it's up here, but this will, of course, show the same result. I just have to wait for it. Let's see whether I did everything right, because yesterday I did the 5-hour subtraction wrong. Okay, it's going. And I should come up with the right key. So, yeah, the passwords are generated. I told you that they are generated on the time function. So we just take the 32-bit value. Okay, there it is. You see it? Guess secret. PG0NE_OL, which is exactly the same that we have here. So we now have brute force the secret, and now we use a second tool that we have written. We just go after, let's first show you the difference. We just ping the firewall, 194.221.6.149. Okay, we don't see any results because everything is filtered, like we saw in the policy before. Show it again. That's here. Okay, the second rule from the top is exactly the rule that prevents pinging from working because all packets are blocked. What we're going to do now is we use the FW1 SKey tool, which is basically an implementation of the protocol that I showed you before and does SKey authentication. So we say, okay, we are 194.221. We want to attack the .149 address, which is the firewall on the NT machine. We want to impersonate as 221.6.159.159, and the secret is PG0NE. Oh, I'm sorry. Thanks. PG0. Yeah, it's the American keyboards, you know. It's a bit different from the German keyboard. NE underscore, an underscore in the right place, OL. Okay, that should do it. Now we will just start the whole protocol that we showed you before, like sending IP addresses, receiving IP addresses and everything, and doing an unload command. Here's what you see. We send version 3.1. We send the command 000C, which is an unload command. We send our IP address, well, not our IP address because we want to impersonate somebody. We send the IP address of the module that we want to impersonate. We get a version back for 1, so it will agree on, the whole mechanism will agree on the lowest protocol version. We will see the address of the firewall, .149, which is also very interesting because up to now we haven't done any authentication and we already know the interface of the firewall. It tells us that it wants authentication SKey. It sends us a challenge of 96. Like I said before, challenges start with 99. We unloaded it sometimes, and now it asks for 96. But we know the shared secret, and we can respond to the challenge. It sends us OK, and then we can start the unload command. We send scope information. Scope information tells the firewall what we want to unload on which machine, which is basically the IP address of the Windows NT machine. We send interface information that tells the firewall which interface we want to unload the information from. This is simply all directions on all interfaces, and we receive a return code 0, which means success. We send a command of 0 to end the connection, and everything is done. And we will now see that we are able to ping the firewall because the security policy has been unloaded. Okay, this was ST. So the problem with ST is that if you use something more secure like FWA1, you were, until version 4.0, you were only able to do that if you had an encryption license. If you didn't have an encryption license, it would automatically fall back to ST. So you would get the warnings and the log file saying falling back to ST, no encryption license. So what people did is they recommended, you can see that on a lot of websites, to use FWN1. FWN1 is an algorithm that was apparently exportable. I don't know why, what the exact difference in exporting restrictions was for FWN1, but it was always recommended that you use FWN1, which is the second authentication method, because it was more safer than SKey. As you have seen, SKey is not very safe. So people recommended to use FWN1. Okay, during our consulting, we came across some FWN1 things and we said, Jesus, we have to do something against that. And that's what we came up with. That's how FWN1 works, FWN1 authentication. So it's again a shared secret between left and right. You do that with FWPut key. And as soon as you connect to the firewall and to the filtering module, and it has shown to you that it wants FWN authentication, it sends you a random number of 16 bytes. To make sure, to enable us to authenticate the filtering module, it does the following. It creates some sort of signature. It's a symmetric signature. It's not a public key thing. It's just a symmetric signature. It's basically a keyed hash. A keyed hash means you hash the data that you want to authenticate, which is concatenated by a secret key. This is what I've written down here in the second line. It generates a signature 1 S1 by concatenating the random number and the secret key K. So it just puts those things together and creates a cryptographically strong hash that is MD5 of that. So what we get is, we get a signed R1, and we are able to verify the signature because we know K as well. So we just do the following. We receive the random number, concatenate K, calculate the hash over those two, and compare it with the signature that the packet filter sent us. So now it expects us to do the same thing. It expects us to generate a random number R2 and sign it as well. So if we are a legitimate management station, this is not a problem because we know K, but we don't know K because we're not legitimate. We're not a legitimate management module. What we do is we have to find a way to do that, to calculate the reply without actually knowing K. And what we do is pretty trivial. We just use the same R2 as we just replay everything. We just receive R1 and don't generate a random number of our own, but we reuse R1. We just, instead of generating our own R2, we reuse R1. And of course, if we reuse R1, we can reuse the signature. So we just take the signature S1, and instead of calculating S2, we just replay S1. And this is what I'm going to show you now. Okay, it needs some setting up because I didn't manage to get this running, and because we had some technical problems before, I didn't manage to get this running with the IP440. So we'll have to show with Windows NT. I'll have to show it to you with the IP440. So let's just add a rule that denies traffic to the IP440 as well. We have that here. We disable that rule. We don't need that anymore. We install that policy here. Oh wait, just let me switch on FWN1 authentication. If you go to lib, edit control.map, some of you know this probably, and say that, okay, anybody coming here. So this is now a bit of doing this with smoke and mirrors, because like I said, we have a technical problem, but the principle will be shown. So we make that FWN1. Okay, just for safety purposes, stop and start the firewall. FW stop. Oh, it's in. Don't get irritated by the German error messages. FW stop. FW start. So now we have, for the unload command, we have now configured FWN1 authentication on the IP440. So we will this time attack the the IP440. Okay, so let's see whether this actually works. Okay, it's fine here. Okay, so let's first naively try to ping the firewall 159. Oh, it works because we have not uploaded the policy yet. So we have to restart the graphical user interface and upload the policy. Also editor. Log in here. Policy, install the new policy. Okay, everywhere. This takes a while. I don't know why. Didn't have any time to investigate this. Okay, policy was installed here. So now we naively go there and try to do the same FW1 S key thing, but the other way around. This time we want to authenticate with the IP440. So it's deny. Oops. So I didn't change the control map accordingly. Like I said, we had to go through some trouble. Let me look again at the control.map file. Oops. It's not there? Oh, it's in lib. Yeah, the notepad command is still called notepad command on the German version. So there, it's none. FWN1. Where did we go? We went to the 159, which is the IP440. Oh yeah. I've been changing it on the NT machine. Of course I have to change it on the IP440, sorry. That's where we go. That's where we have to change it. Okay, let's go to... So like I said, we have to fake this a bit because the thing didn't work from the beginning. FW stop, FW started. So it accepts the new authentication model. Okay, it's coming up there, so we have to reboot we have to reload the rules, management clients, policy, everything here. Okay, everything is run. Connect into the server. Okay, install the policy. Let us safe and sorry.
To his credit, Thomas is not actually checkpoint CCSA or CCSE. He just knows how to break them.
Okay, like I said before, we tried naively to play the S key trick, and now it demands, now it's FWN1, and now we say great, because it's even simpler. We go here and say, use our different tool, FW1, FN. So what we have to do is just specify the firewall that we want to unload. Oh wait, let's first ping the firewall to show you that the security policy is really loaded. .6.159. Okay, nothing comes back. And now we are going to unload the policy, 159, 194.221, 149. So we are contacting 159, which is the IP440. We are acting as if we were the 149, and we are authenticating here. And as you can see, the random number we receive is just the random number that we sent back. The signature that we receive is just the signature that we sent back. It says, okay, authentication done. Scope information, the rest is the same. And we are able to ping it. And you see, it's pinging. Okay, so now we upgrade the whole thing to FWA1. Okay, I stop the firewall. Okay. Restart the GUI as well. everything done. Okay, FWA1. Looks like that. It's very similar to FWN1. We get sent a random number R1, and we get sent the same signature again. So, but this time, the firewalling module does not expect us to only send back a signed random number, but to send back a random number and not sign our random number, but their random number XOR. So that is what that character is used to express. XOR the random number that the server has sent us. So what happens normally? The server sends us a random number, we generate a random number, XOR those two random numbers, send back to the server, to the firewall module, our random number and the signature of the set XOR between of the XOR of its random number and our random number. Okay, what do? Of course, we choose our own random number to be 0, because the server's random number, XOR 0, is again the server's random number, and we can reuse the signature. So we again have the shared key. We just choose R2 equals 0. So in this way, R1 XOR R2 equals R1, because anything XOR 0 is anything. And in that way, we have the signature 2 is a hash of R1 XOR R2, a signature of R1 XOR R2, which is by replacing R1 XOR R2 by R1. It's just a signature of R1, and that's what we got from the firewall module. And this is what we can use to circumvent authentication. But this time, we have an additional problem. I've been lying to you. It's not only being used for authentication, the hash, but only the lower half of the hash, the lower 64-bit, are being used for authentication. The upper 64-bit are used to negotiate an encryption key. So if the authentication is successful, from there on, the whole thing will be encrypted. So that's why you see down there to be solved encryption. We don't know how to do that. At the moment, we are able to circumvent the authentication, but we are not able to break the encryption. So we can't unload everything. I can just show you that we can get past the authentication, and well, the encryption thing probably needs some work. I can just show you that we can get past the authentication. We will not be able to unload anything, but I can show you what it looks like. We just say use our next tool, FWA. We go through it, and yeah, we see authentication method FWA1. The authentication method that we get is actually a hex number what we receive. So we receive a random number, which is the long number, the second long hex number, and we get the signature up there. And what we send back is we set the random number to 0 and just copy the signature. We get an OK back, but as you see, the state is not 1 anymore, but it's already encrypted. So one of our first thoughts was it's encrypted using FWZ1, which is a stream cipher. So if they use the same key in both directions, then we could just XOR that value with the value that we know it has, with a plain text with 1, and would get the first 4 bytes of the key stream, which would us in turn enable to just use these 4 bytes of key stream to encrypt information that we want to get to the firewall. But unfortunately, 2 different keys are used in both directions, so this doesn't work, and we currently don't have any method to successfully attack FWA1 apart from the authentication part. So FWA1 for the time being is safe against attacks by us. But still we could get past the authentication. Yeah, the encryption thing is quite interesting because the algorithm, it's FWZ1. The algorithm is proprietary. It was developed in the beginning of the 90s because back then there weren't any standards for IP VPN computing, and the algorithm was not made public, but it has been made public. During last week, it was posted to SciCrypt, to the newsgroup SciCrypt, and since then, I expect people will be picking it apart, and time will show whether it's still state-of-the-art, the FWZ1 encryption algorithm. But up to now, no weaknesses are known, and it seems that FWA1 is currently immune against those attacks. Well, another attack might be possible. We are investigating this because what we are getting is a random number and a signature of that random number. So what we might be able is if the key that is used to make the signature doesn't contain enough entropy, we will be able to, just having the data and the signature for the data, we will be able to brute force the key. Because we can do that offline, we don't have to do this online. We can try to brute force the key, and just by looking at the data, that is the random number, and the signature of it. So the future will show whether this is anything promising, but this is FWA1 authentication. So these were the attacks on the intermodule authentication. We will now switch over to attacks against the filtering mechanism itself. FireWall1 is stateful inspection, and there's quite some ways to circumvent the filtering rules that you have configured. On the one hand, this is quite common misconfigurations for FireWall1, and on the other hand, this is implementation errors. You always have to make a difference between those two. And yeah, we're going to show you from now on what we have in our hands against the FireWall1 filtering method itself. So, what time is it? Do we already have to move, or? Okay, so we only have time till 2:40. So I think we will have to move now to another room. That's why we have brought our own table. We'll just disconnect everything from the stage here and then carry it over to the deep knowledge track.